start with the definition of a dot product here. So here's your definition of a dot product. It starts with two vectors, u and v. And then we're just going to label the horizontal and vertical components for those two vectors. So u is u sub 1, u sub 2. V is v sub 1, v sub 2. And then on that second line there, that's the word for a dot product. As you're writing it down, you can see why it's called a dot product, because it looks like u dot v. In order to calculate the dot product, you basically multiply the horizontal components, u sub 1, v sub 1, find their product, and add that with the product of the vertical components, u sub 2, v sub 2. When you multiply these components and add them together, your answer is going to be just a number, right? So, important thing to know about the dot product, your answer is a scalar. It is not another vector. So when you use the dot product to multiply two vectors, your answer is not a vector, rather just a number. Now we'll look at an example, and again, the nice thing about this is if you can recognize in the directions that it's asking for a dot product is not necessarily challenging math. It's pretty easy. So we want to find the dot product for these two vectors. Now your vectors can be written in component form with the angled brackets and the comma. It can also be written in linear combination form. So I want you to feel more comfortable with both forms. And you can go in and out of forms if you want, but my hope would be you'd be comfortable using either set. So we have u is negative 6i minus 3j, and v is negative 8i plus 4j. Follow the work for the dot product above. U dot v equals your horizontal components are just the coefficients to the I, so we would do negative 6 times negative 8 plus the product of your vertical components, which would be negative 3 and positive 4. So you come up with something like 48 minus 12. So u dot v is 36. You have a dot product. Any questions about that calculation? When you add vectors, when you subtract vectors, when you do scalar multiplication, your answer is another vector. When you do a dot product to multiply vectors, your answer is just a number. Okay, now you don't have to write these down. Okay, so on this slide, just kind of look up at the screen, follow along with us. If you want to write anything down, you can write that properties of the dot product show up on page 431. Okay. All these properties say is that like these two things are the same. Okay, so you could do the left or the right, and you'll get the same answer. Dot products, we might say, are what we call like commutative. It doesn't matter if I do u dot v or v dot u, I'm going to get the same answer. And if you think about that math that we just did, if we flip-flop those two vectors, I mean, we're still going to get the same products and the same sum, so it doesn't matter what order I'm doing the dot product. If I take 0 times a vector, or 0 dot a vector, it's going to be just equal to 0. Okay, so that would be pretty simple. Here, this is like basically like your distribution property. If you were to take two vectors v and w and add them together, remember you just like add your horizontal components, add your vertical components, and then do a dot product with u. It would be the same thing if you did the dot product with v and the dot product with w and then added them together. You're probably, if you see a problem like this, you're just going to do this side, and that's okay. It's just a property telling you that those things actually still work. Okay, so you could distribute the vector to v and w. 4 is kind of an interesting one, so I'll just look at it. Again, it's not really necessarily something that you have to memorize, but good for you to see. If you were to do a dot product of a vector with itself, it's going to equal the magnitude squared. And so we'll kind of look at what that would mean. Suppose v has components v sub 1 and v sub 2. If you were to do v dot v, you would take the horizontal component v sub 1 times itself, v sub 1, which would be v sub 1 squared. And then you would add to it vertical component v sub 2 times vertical component v sub 2, so that would be v sub 2 squared. Now, anytime you see v sub 1 squared plus v sub 2 squared, you probably think, I've seen that before, it looks a lot like magnitude. So magnitude of v, remember, is the square root of v sub 1 squared plus v sub 2 squared. Since there's no square root, it's really like we've squared both sides. So v sub 1 squared plus v sub 2 squared is really equal to the magnitude squared. And that's the property that they're giving you. Okay. So just something interesting. And then the last one, this one is a little bit different than number 3. Notice you have a c, which is not another vector, it's a scalar. And so you're taking a scalar times a dot product. You probably would just do the dot product first and then multiply by the scalar. Okay. This is the same thing as multiplying one vector like u by the scalar and then doing a dot product with v, or multiply v by the scalar and then do a dot product with u. But notice on this one, you don't multiply both vectors by the scalar first, because you don't distribute over multiplication, you only distribute over addition and subtraction. Okay. So those are just interesting things to look at. They're nothing that you have to have memorized, but they're things that as you work with vectors more, you start to see these patterns exist. Okay. All right, this you'll want to write down. We're going to use the dot product to find the angle between two vectors. And it's got a formula there. This formula will show up on your quiz and test, meaning you do not have to memorize this particular formula. But you do have to be able to use it. Okay, so this angle is different than the direction angle. Remember that the direction angle is like the angle between the vector and the positive x-axis, so it's always between 0 and 360, like an angle in standard position, going one time counterclockwise. this is not between a vector and the positive x-axis. This is just between two vectors that could be anywhere around the coordinate plane. Okay? And so in order to find the angle between the two vectors, you're going to do the cosine theta equals, and what's this on top? U dot V. That's the dot product. Okay? So think about, for this formula, you need to know in the numerator I'm going to have a dot product. And think about what happens when you calculate a dot product. When you calculate the dot product for U and V, you're going to have just a single number. So there's going to be a single number in the numerator. Okay. In the denominator, what are these representing? Magnitudes. So the denominator is the product, meaning multiply, of the magnitudes of U and V. So we know how to calculate magnitude, square root of v sub 1 squared plus v sub 2 squared. We'll have to do it for U and V separately and multiply them. Now, if you want to do this all in your calculator at one time, the only thing you'll have to be real careful of is the fact that you're multiplying in the denominator, so you need that multiplication to happen before the division. So you would use a set of parentheses around the magnitudes if you're going to not multiply them first. And then finally, to solve for the actual angle, you'll still have to arc cosine or inverse cosine both sides. Because you're taking the inverse cosine of both sides, what are the possible values for theta that we're going to get out in the calculator? What does inverse cosine let you get in the calculator? 0 to 180. Okay. So when we find the angle between two vectors, we're going to get an angle between 0 and 180, which means we're finding the smallest angle between the two vectors. I'm going to show you what that means. This formula finds the smallest angle between two vectors, and the smallest angle between two vectors is between 0 and 180. That makes sense because we're doing the inverse cosine. Okay, that's all that the inverse cosine would give. And then to visualize that for you, I'm going to draw two vectors. I'll get a vector U and a vector V. If I use this formula to find the angle between the two vectors U and V, the angle that it gives me, because I'm doing inverse cosine, is going to be between 0 and 180. So I'm going to get that smaller angle between the two vectors. Okay. I'm not going to know this larger angle between the two vectors. Well, we could get that by subtracting from 360, but note that there are multiple angles between the two vectors. And in fact, there are infinitely many. We could start at U and do a whole rotation and then get to V. So it's always going to give you the smallest angle between the two vectors. And then the last thing on this slide, just real quickly, if your angle between two vectors is 0 or 180 degrees, then the vectors are parallel vectors. If the angle between the vector is 0 or 180, the vectors are parallel. Think about it in that picture. If you had a 0-degree angle between two vectors, then they must share the same initial point, so it's like the vertex of the angle. They must be going in the same direction if they have a 0-degree angle in between them. Okay, so they're following the same direction. If those two angles have 180 degrees in between them, what can you say about the direction? Opposite directions. Thank you, Abigail. So in terms of like this idea of parallel, remember that they are really sharing initial point because we're finding the angle between the two vectors. So we're saying same direction or opposite directions for 0 to 180. Now, let's do an example so you can see this formula put to use. You will need a calculator, so get out a calculator if you've got one with you today so that you can practice typing this stuff in. Remember, like, the math is not necessarily challenging math, but it's, can we do it? Can we follow the formula? Can we get the right answers? Those are the questions we've got to ask ourselves. So we're going to find the angle between the two vectors u and v, and u is negative 6i minus 3j. V is negative 8i plus 4j. Is that the example we did before? Oh, it's the same example. So that's my example from the dot product. Okay, so what's nice about this one, since we did this a couple slides back, what is the dot product of u and v? 36? Okay. Now, if you didn't already have the dot product, you have to do the dot product, right? Horizontal times horizontal plus vertical times vertical component. What else do we need for our formula to be able to calculate the angle between the two vectors? Magnitudes of each. Okay, so we need the magnitude of u, and we need the magnitude of v. So for magnitude of u, I'm going to do the square root of, and then negative 6 squared would be 36. Negative 3 squared would be 9, so that's the square root of 45. And then for magnitude of v, that would be this negative 8 squared, which is 64, and 4 squared, which is 16, so square root of 80. Now, normally, I would press you to always make sure your radicals are simplified, but that's when your answer, your final answer is in radical form, because these radicals are just going into a formula. You don't really need to simplify them, because you're going to, like, inverse cosine everything. So I really don't take the time to simplify these radicals. I'll just put them into my formula. And it makes it a little bit easier to type. Cosine of theta then is equal to 36 divided by square root 45 times square root 80. If you want to just use your calculator right now, you can inverse cosine both sides. You'll just have to make sure that you put a parentheses around square root 45 and square root 80 in the denominator. Okay. The other option you have is, because they're both square roots, you could multiply 45 and 80 and have just a single square root under there. So type that in, and we'll see if we all get the same answer. Inverse cosine both sides. Anybody get an angle? Q? 53.13. Anybody second that? Lauren, Elise? I think that sounds right. Okay. Now, just to kind of help you with this, I'm going to real quick draw a sketch. You don't have to do this every time you calculate the angle between two vectors, but because vectors are a very visual thing, it's kind of nice for us to think about this every now and then. So I'm going to real quick over here on this side sketch out u and v. U is negative 6, negative 3. Left 6, down 3, there's u. V is negative 8i plus 4j. That's 8 to the left and 4 up. V is somewhere up here. Does the smallest angle between those two vectors look like it could be 53.13 degrees? That seem reasonable? Yeah. Any questions about finding the angle between two vectors before we move on? Okay. One more thing regarding the angles between vectors is, we talked about parallel vectors where they're going in the same direction or they're going opposite direction. Right in the middle of that are orthogonal vectors. Those are vectors that are perpendicular. So orthogonal is another word for perpendicular. What does perpendicular mean? Forms a right angle, right? So we know that it's 90 degrees. Think about that formula that we just looked at. The cosine of theta is equal to u dot v divided by magnitude of u times magnitude of v. And let's imagine that we knew the vectors were orthogonal or perpendicular. That would mean that theta was 90. So we're thinking about the cosine of 90 degrees. What is the cosine of 90 degrees? 0. So when you're looking at that formula, and you're looking at this side right here, u dot v divided by magnitude u times magnitude v, what's the only way that fraction can equal 0? Well, if the angle's 90, but specifically in the fraction, the dot product and the magnitudes, what has to be true about all ones? The dot product has to be 0, right? That's the only way a fraction equals 0 is if the numerator is 0. 0 divided by a number. Okay. So a shortcut to finding out whether or not two vectors are orthogonal is just checking their dot product. If the dot product of two vectors is equal to 0, then in that formula you're going to have 0 divided by some magnitudes, and it doesn't matter what the magnitudes are, it's going to be 0, and then the inverse cosine of that is going to be 90 degrees. So vectors u and v are orthogonal if and only if u dot v is equal to 0. And so this is one of those things where, like there's multiple ways to do this. I wouldn't count it wrong if you use that cosine formula, and I've had students do that in the past. If I ask if these two vectors are orthogonal, people will be checking for a 90-degree angle, so they'll do the full formula. And if the formula equals 90, they say yes. If the formula doesn't equal 90, they say no. But those of us who recognize the shortcut, the only way that's going to equal 90 is if the dot product is 0, so let me just calculate a dot product. U dot v. Multiply my horizontal components, 6 and negative 1/3. Add to that the product of my vertical components, 10 and 1/5. That'll be negative 2 plus 2, which is 0. So yeah, they're orthogonal. If you get any other number besides 0, your answer is. So that is a lot less work than doing the cosine formula. You'd have to do the dot product, then you'd have to do the magnitude of u and the magnitude of v, and then do the whole inverse cosine bit. All right, we've got one more topic to discuss, and that is the topic of work. Okay. So my physics students might recognize this work formula. Okay, those of us not in physics, here it is. Work can be calculated as force times distance. You having a little celebratory party back there? Is this your favorite?
No, I just know it.
Oh, okay, excellent. And maybe in physics it's possible that you use like work equals just like F times D. I know you guys shorten everything.
Yeah, it's F times the displacement delta.
Yeah, oh yeah, you guys call it displacement, that's true. Okay, so in physics you might call it displacement. In math we just refer to it as distance, but they mean the same thing, right? A change in distance or x. Okay. And then I'm going to add one thing to this formula about the force. The force is not the total force, but really the component force in the direction of the motion that's happening to the object. Okay, so I'll give you a chance to write that down and then we'll talk about it. Okay, so when these are examples that we're going to be looking at, like where we're moving an object. We might be pushing or pulling or like lifting, like a pulley system type thing. And so what happens is as you do the work, you are applying some kind of force to the object at hand. So imagine me like pulling the wagon. Okay, I have some force on the handle so that I can pull the wagon or some horizontal distance. Well, as I'm pulling the wagon, I have vertical and horizontal components of my force. But if I want to look at how much work I did to move the wagon horizontally, the only force that's working there to move my wagon horizontally is my horizontal component of force. So rather than multiply by just like regular force, I have to pick out the exact component of force that I want. So if you're moving something horizontally, you're going to use your horizontal component. That's going to be your force times cosine of the angle. And if you're moving something vertically, you're going to pick out the vertical component. That's going to be your force times the sine of the angle. Okay. So I have an example, and this example actually comes from the textbook. It's on page 439, and it's number 84. So if you want to jot that down, and then, rather than write out the whole wording of the word problem, maybe jot down a few key pieces or draw the picture of the guy with the rescue toboggan. You can decide which one to put in your notes there. But you can look back in the textbook if you need to see the full thing. So you've got a ski patroller pulling a rescue toboggan across a flat snow surface, exerting force of 35 pounds on the handle. It makes an angle of 22 degrees with the horizontal, and we want to find the work done by the ski patroller if he pulls the toboggan 200 feet. Okay, so just like yesterday when we looked at that, it was in our notes, the example with the water balloon, and we had initial velocity. Initial velocity and force, those are going to be your magnitudes. So where I know that my force is 35 pounds, that would be the magnitude of my vector here, okay, that I'm using on the handle. And I want to find the work done for pulling the toboggan 200 feet. So that's going to be my distance, or what you might call displacement in physics. Okay, so I'm moving it 200 feet. And then to calculate the work, I want to do force times distance, but because I'm moving it horizontally with the ground, I want the horizontal component of force times distance. So the force is 35 pounds. What's the horizontal component of force? 35 times the cosine of 22, right? You're thinking about putting it in component form. So you could, over here in component form, you'd have 35 cosine 22 and 35 sine 22. Because we're pulling the toboggan horizontally, we're going to pick out the horizontal component of force there. Okay, because that's the part that's doing the work of dragging the toboggan. So we would say work equals 35 cosine of 22, and then our distance is we're moving the toboggan 200 feet. I believe that comes out to a fairly large number. 6,490.29. And then here's the other part is, remember in a word problem you should always be labeling things. Does anybody remember, like in physics, what labels you used a lot of? Newtons, joules, Newton meters, those type things. Okay. We're going to use the labels that we had in the problem. So for the work, that goes with our force, and our force had a label of pounds. So this is pounds, and then we're multiplying it by our distance, which has a label of feet. So for our label, we call that foot pounds. And I know like that's not like the nicest label, but all you'll have to do is read like what's the label for my force, what's the label for my distance, and then that's going to be my answer. If you wrote pound feet, that's fine. What we call foot pounds. Okay. Any questions that I can answer for you? You have a homework assignment in the textbook. Do that homework assignment so that tomorrow you can really work on the review and kind of tweak those like last minute questions that you have before you take the quiz.